We have another router. Let's say this one is in Nigeria. I'm going to use, and this one is in Ghana. This is Ghana. So there is a local area network in Ghana. I mean, in Nigeria. This is a LAN here. There is a LAN in Ghana also. I mean, there are people connected to this. Is our switch. People connected. People are connected. And we want to link the router in Nigeria to the router in Ghana. So most of the time, you see us put this sign. I explained that when we had our static route stuff. Sometimes you see this sign, which is the sign of the cloud. This connection altogether is what you refer to as wide area network. What is in this cloud or what is in this connection? That is what my video is all about. I sent a video on wide area network and I sent video on IPsec VPN because we can get this job done with dedicated wide area network, which was fully explained in that video, or we can make use of internet. As long as Nigerian router has access to the internet, regardless of the service provider they are using, and the router in Ghana also has access to the internet, it doesn't matter the service provider in use, we can use this technology called IPsec VPN to link the two routers together. And with that, we build wide area network. But because Nigerian router can see Ghana router, does not mean that this LAN can talk to this LAN. And that was why we went into static routes in the last class. You remember we talked about routing concepts. Routing concept. Because Nigerian router does not know about this LAN here. Ghana router does not know about this LAN here. Even though they can talk directly, they don't know about their LANs, various LANs that they are connected to. That's why we went ahead and did static configuration to inform Nigeria router manually about this LAN and then inform Ghana router about this LAN. And we did that in static route. And we went through different types of static route. But that is static. When I was teaching you guys this routing concept, I said you can do this thing manually, which is statically, or you can do it dynamically. So the one of the ways to execute this or to implement this dynamically is by using a protocol called OSPF. Another one is called RIP. Another one is called EIGRP. EIGRP. RIP is dead. It's resting in peace. We don't use RIP again. EIGRP is no longer in CCNA, it's in CCNP. So the only dynamic routing protocol that we're going to be exploring in this class is OSPF. So what that means is this. By the time we are done and we go to the practicals, we are not going to use static routes informing the router in Nigeria manually about Ghana LAN, or informing the Ghana LAN about Nigerian LAN manually. No, we will allow them, we will just set up the protocols and allow them to sort themselves out. That is what today's class is all about. So we may not be able to get to the configuration because I want to take my time and talk about the theory, but I don't know. I can switch in between the two. Let's see how it goes. Yeah, BGP is exterior gateway protocol. It is used to link different autonomous systems, like two different banks or two different companies, or when you want to connect different service providers together. We don't use BGP within autonomous system. That is within a company. All of these ones I mentioned here, they are called interior gateway protocols. Interior, because you can use them within the organization. But BGP is exterior gateway protocol. You can use BGP to link different service provider or different organizations together. So we don't, BGP is also in CCNP briefly, but more of BGP. If you want to see more of BGP, you go into CCIE. I did a lot of BGP when I went for my CCIE in India. So all of these protocols, I can talk about them in depth, all of them. But in this class, we are just going to be talking about OSPF. That is the only one we're going to learn. It's the only dynamic routing protocol that we're going to learn. So it therefore means at the end of this CCNA program, you should be able to implement OSPF, which is the only dynamic routing protocol we're going to be learning, or your static route. And when I say static route, I'm talking about the varieties of static route, the standard route, the default route, the host route, and we did all of this. Either way, you need to know all of this properly. I hope I communicated, give you the background of what we are about to do. So let's proceed. So the topic is single area OSPF version 2 concept. Single area OSPF version 2. So why did they say single area? You are going to see why. Why did they say version 2? Because we also have version 3. So we are going to talk about the concept of OSPF in general. Then we limit it or narrow it down to single area because you can have multiple area. We narrow it down to version 2, and later we narrow it down to version 3. And we're going to learn how to configure it at version 2, the one of version 2. Anytime you hear version 2, most of the time, it's talking about IP version 4, a protocol that works with IP version 4. And when you hear version 3, you're referring to the one that works with IP version 6. So what are the objectives? You can see the objectives here. We're going to talk about the OSPF features and characteristics. So we'll talk about the features and the characteristics of OSPF. We're going to talk about the OSPF packets, different type of packets used in single area OSPF. We're going to talk about OSPF operation, how a single area OSPF operates. OSPF features and characteristics. So what is this OSPF? Let's learn the introduction. OSPF is a link state routing protocol. Take note of that. OSPF is a link state routing protocol. Why did they call OSPF a link state routing protocol? I will show you that. I will explain that. That was developed as an alternative for the distance vector routing protocol RIP. So they develop OSPF to replace RIP. Why do they need to replace RIP? It's because of the way RIP operates. OSPF has significant advantages over RIP. How? In that it offers faster convergence. What do we mean by faster convergence? When you set up everything, all the routers on the network, for them to get to know about all the networks all over. If you are running RIP, it takes forever. If you are running OSPF, everybody knows about all the networks as soon as possible, or as fast as possible. So OSPF is very fast. Anytime you hear convergence in networking, it's talking about synchronization. That's another word for it. Everybody get to know about all the networks all over. And it can scale to a much larger network implementation. OSPF can support a very big network. For RIP, once you have more than 15 routers on your network, you can't use RIP. RIP has that limitation. It can support maximum of 15 routers. What if you have an organization where they have like 250 routers? You cannot use RIP in that kind of organization. But OSPF doesn't have that kind of limitation. So that is one of the reasons they got rid of RIP, and then they now marketing OSPF. OSPF is a link state routing protocol that uses the concept of areas. It uses the concept of areas. What do I mean by that? That is another way of segmenting the network at layer 3. You know, when we segment our network, before I tell you, you just drop a router, you have different connection to the router. But in the context of wide area network, that's another way of segmenting. You're going to see what I mean by that. A network administrator can divide the routing domain into distance area. That helps control routing of the traffic. Why? Because you have different area. Just follow me. You know, I have a way of connecting the dots later. You know, sometimes when you're teaching a new concept, a new technology, people look at it like you are speaking Latin. Don't worry, we're going to connect the dot. A link, take note, a link is an interface on a router. A link means what? It means an interface on a router, which is also a network segment that connects two routers. So if I have a router now, and I have another router here, there's a port here, there's a port here. If I link these two routers together, this is a link here. That link simply means an interface on that router. It connects the network, other segment, the two routers together over a segment. They form a segment together. Or a stub network such as LAN that is connected to a single router. If I have another connection like this to a switch, this is a link here. This one connecting to a switch here, as long as you have one exit out of your network, it's referred to as a stub network. I think I've mentioned that before. I'm also going to show another example of that. Information about the state of a link is known as link states. So when we tell you that OSPF is a link state routing protocol, what does that mean? It's a protocol that gathers information about the link, displays information about the link. There's all kinds of things about the link. What kind of information does it display about the link? Look at it here. All link state information includes network prefix, that is the network address, prefix length, that is the subnet mask or the slash notation, and the cost. We talk about cost in the under spanning tree protocol. The same concept here. If I'm going to so destination, what is my cost to that destination? And that is based on bandwidth. You're going to see that. So these modules covers basic single OSPF implementation and configuration. So we're going to talk about single area. We can have multiple areas, but that is covered under CCNP. For those that don't know CCNP is just the advanced level training or advanced course or training of CCNA. So you need to be aware of that. CCNP is higher. OSPF features and characteristics. Components of OSPF. All routing protocols share similar components. All of them. They all use routing protocol messages to exchange route information. What does that mean? The message helps build data structure, which are then processed using a routing algorithm. Let me tell you something before we proceed. You need to understand it. I'm going to take my time to finish this chapter. I may not go into any configuration until the next class. If I have a router here, I have another router here. I have a local area network here, another local area network here. And of course, there's going to be a network address for this place. And there's going to be a network address for this place. Let's say this router is in London. And this one is in Germany. I link these two routers together. Again, go back to my wide area network video and IPsec VPN. Let's call this one LAN A. And let's call this one LAN B. How will London router get to know about LAN B? And how will Germany router get to know about LAN A? Because they are not directly connected. By the time we implement OSPF, do you know what is going to happen? London router will form neighbor with Germany router. They will form friendship. Then London router will now say, Germany, do you know what? There is a LAN under me. Automatically now, we are not involved. We are going to get involved briefly, but then after that, we'll leave them to continue from there. Unlike what we did with static. Do you know what? There is a LAN under me. There is a LAN under me. This is the network address of the LAN. This is the subnet mask. And in case you have a message for that LAN, send the message to me. Germany router will also say, oh, hi, London. We are friends now. Do you know what? There is a LAN under me called LAN B. This is the network address. This is the subnet mask. And this is how you can reach it. You can reach that LAN through me. The two routers will exchange information about remote networks automatically. They will exchange information about remote networks automatically. And guess what? This is the beauty of dynamic. If this LAN goes down, London router will update Germany, say, guy, I told you that time there is a LAN under me. You know what? The LAN is dead. Don't bother sending any message to me. If the LAN comes back again, maybe this interface went down or the cable, London router will update Germany router. That LAN that I told you that died that day is now alive again. If you have a message, you can now forward to me. That is the beauty of dynamic. But if it is static, if this LAN dies, we have to go to the Germany's routing table and remove it manually. When it comes up, we have to go to the routing table of Germany router and put it again manually. Dynamic routing protocols do not operate that way. They sort themselves up automatically. We just get involved at the initial stage and leave them to sort themselves out. That is the beauty of dynamic routing protocol. So when they say they use routing protocol message to exchange routing information, they talk to themselves about remote networks. They exchange information. If there's any updates, they will always sort themselves out. Network goes down, they will tell themselves. That network is bad, they will inform themselves. That is the way dynamic routing protocols operates. Router running OSPF exchange messages to convey routing information using 5 types of packets. This is why people don't like OSPF. Who is disturbing me in there? This is why people don't like OSPF. OSPF has too many stories. If I'm going to teach you guys RIP now, sharp, I'm done teaching you guys. Even here at JRP, sharp, I'm done teaching. But the moment we start talking about OSPF, BGP is even worse. It's endless. The moment we start talking about OSPF, so many things to talk about under OSPF. And that is why I want to just use today's class. Maybe if you are getting bored, I will give you a break and then do some demonstration briefly with one small topology. Then we'll continue the stories. So many stories to talk about here. So when the router starts running OSPF, there are different types of messages or packets they use. Number one is called hello packets. Number two, database description packets. Number three, link state request packets. Number four, links update packet. Number five, acknowledgement packet. What are all these packets? Why do they have different tag or different description? It's just like me writing a letter to you. You can call one letter message of love letter. You can call another letter. You just like title. When you give a title to the letter. So depending on the message or the content, that is the way this packet. Take for instance, what is hello packet? We're going to talk about that now. It's one of the packets that these routers will exchange between themselves, depending on the information they want to pass across to themselves when we are running OSPF. So these packets are used to discover neighboring routers and also to exchange routing information to maintain accurate information about the networks. So what are these packets that they exchange between themselves? Let's check them out. I think, sorry, just a minute. Let me see. There should be a place for those. Okay, let's continue then. I will play some video for you guys and I will come and expatiate more on those packets. So take notes. There are 5 packets they used to talk to themselves. Hello packets, database description packets, link state request packets, link state update packets, link state acknowledgement packets. So these routers will be sending either of these messages to themselves, of this packet. I was still going to come to that. For instance, hello packet. What is hello packet all about? Hello packet is just to keep track of your neighbor. And there is a period That's what I mean by duration. It's like me saying, guys, every 5 minutes I'll be telling you, give me 777 if you're still hearing me. So every 5 minutes I'll say, give me 77. That is the LO packet. I'm just keeping track, making sure that you guys are still there. And you guys respond back to me. You respond back to me. LO packet is just to keep tracks between the routers. Database description packet, you see what it does. Link state, you see the purpose of link state, and so on and so forth. So each of these packets under OSPF, you need to know what they do. If you have question, it's like somebody, if you have question, please, you can raise up your hand and let me know. Can I proceed? Am I communicating, guys? Okay, okay, good, thank you. So we're going to come to that. We're going to come to more of this stuff. So let's just continue. Still talking about the component of OSPF. OSPF messages are used. Please mute yourself. Mute yourself. Mute yourself. Mr. Oroji, you can help me identify whoever anybody disturbing us so that I can call the name. OSPF messages are used to create and maintain 3 OSPF databases. So all those packets that I mentioned earlier, we've not gone in depth. In the process of exchanging those packets, some information are being passed across. And as those information are being passed across, databases are being built. It's like I'm giving information. You need to keep the information somewhere. So for OSPF, they have what we call adjacency database. Sometimes we use that word table. So when we want to call it table, we call it neighbor table. So anytime you hear us talk about adjacency database or neighbor table, we are saying the same thing. What is going to be in this adjacency database? It is the list of all neighbors routers to which a router has established bidirectional communication. So if a router is here now, another router is here now. Let's say this is router 1, this is router 2, this is router 3. Router 1 will have its own neighbor table. What will be in the neighbor table? It will put this guy's detail. This is my neighbor. Router 2 will have its own neighbor table. What will be in this neighbor table? This guy is my neighbor on this interface. This guy is my neighbor on this interface. So this table is unique for each router because you connected on different interfaces. And how can you see that neighbors table? You issue this command. When we are done putting OSPF, you're going to see show IP OSPF neighbor. You put that command on the router, you can see your neighbor that is directly connected. So if for any reason you are doubting you are connected, your neighbor is still alive, you can check your neighbor out. Another database that is built from this packet is called link state database, which is also the same thing as topology table. What is in the topology table? It lists information about all other routers in the network, not just neighbor now, all the routers. This database represents the network link state database. All routers within an area we have identical link state database, and we can see that database by issuing show IP OSPF database. And the last database is called a forwarding database, which is the same thing as our routing table. You guys are familiar with this terminology, routing table. Under OSPF, we don't call routing table, we just call it a forwarding database. It's the same thing. So what is going to be in our forwarding database? The list of routes generated when an algorithm is run on the link state database. What does that mean? All the different all the different way I can pass through to reach a particular location will be in my forwarding data. The active one actually that I'm used at that point in time will be in my forwarding database. What if I have a backup route? I keep it in my link state database. Is it in link state? Yeah, I think it's in link state database. I can go and pick it up there if the primary link it's messed up. So what you know about routing table before when we did static route is the same thing. And of course, our command remains the same to check the routing table. Show IP route. So in the context of OSPF, you hear us saying adjacency database, link state database, forwarding database, but these are their equivalents and what's the things that are going to be in the database. The router, I prefer it to have been OSPF router. Anyway, since we are talking under OSPF context now, the router builds the topology table using the result of calculation based on Dijkstra shortest path SPF algorithm. This is the guy that wrote OSPF. That's the name of the guy. So most of the time you hear us, especially if you want to write certification, they ask you for the algorithm. For instance, for RIP, the algorithm for RIM that is run on our router is called Bellman-Ford. Bellman-Ford. Then for OSPF is Dijkstra algorithm. So sometimes we say Dijkstra SPF algorithm. So what we are simply saying is this: the router is going to calculate, is going to run that algorithm and calculate the best route or the shortest path to the destination. The SPF algorithm is based on the cumulative cost to reach a destination. And by now, I know you believe you know about cumulative cost. Let me give you an example. We are going to the destination from this router here. Let's say the cost here is cost of say 4, 4, 4. Here is 20, 20, 10. And this is cost is based on bandwidth, just like what we did on that spinal tree protocol. Okay, thank you. So if you calculate the cost on this side, total cost, cumulative cost is 12. Calculate the total cost on the other side, the cumulative cost is 50. This particular router running OSPF, we put this link in its routing table. The other link we put in the link state database as a backup route. And this thing is calculated based on bandwidth, meaning the higher the bandwidth, the lower the cost. The higher the bandwidth, the lower the cost. Don't ever forget that. The higher the bandwidth, the lower the cost. So the SPF algorithm creates an SPF tree by placing each router at the root of the tree and calculating the best paths, best shortest paths. That's the shortest path to each node. That's the different destination now. The SPF, which is shortest path first tree, is then used to calculate the best route. OSPF places the best route into the forwarding database, which is our routing table, which is used to make the routing table. This is how OSPF behaves. It runs the algorithm, calculate the shortest path, check out different destinations, which one is the shortest path, based on the lowest cost, cumulative lowest cost, it installs that in the routing table. That is the part it's going to be using. And I believe you know what we mean by algorithm. You need to check it out if you have issue with algorithm or Google. Link state operation. To maintain routing information. What does that mean? When we say maintain routing information, keep it up to date. Keep it up to date. OSPF routers. When you hear OSPF routers, simply mean routers that is running OSPF. Complete a generic link state routing process to reach a state of convergence. The following are the link state routing steps that are completed by the router. First stage, the router will establish neighbor adjacency. When we have two routers like this, the moment we put OSPF on this router, put OSPF on the other router, the first thing they will do is to form neighbor. They will talk to themselves. If you run OSPF on one side, you are here to put it on the other side. They can't talk as neighbor because they are not both running OSPF. even though they are both routers, but they must speak the same language. You remember we talked about protocols, set of rules. So now the rule now in this house now is OSPF. Or the protocols right now is OSPF, and OSPF has its own set of rules. It's a protocol, just like it's called routing protocol. If we want to route, all of us must be on the same page. All the routers must be on the same page. All the routers must speak the same language. So they must first of all establish neighbor. Then they will exchange link state advertisement. Link state advertisement, you tell me about the state of your link. What are the information you tell me about your link? The network ID, the prefix length, the cost. The next thing is they will build a database. This guy will build his own database. This guy will build his own database. I'm just using 2 routers. You could have more than one. Then the next thing is to execute the SPF algorithm, because it's all about different destination. Okay, if I'm going to this land, do I have more than one route? If it's only one route, okay, I've put it in my routing table. If I have more than one route, which one is the best out of all these routes? And then they now choose the best route. This is the way link state routing protocol operates, especially OSPF. I'm going somewhere. I said OSPF. For this class, we are going to talk about just single area, but you can have more than one area. So what do we mean by single area OSPF? To make OSPF more efficient and scalable, take note, OSPF supports hierarchical routing using areas. What is areas? An OSPF area is a group of routers that share the same link state information in their link state database. Look at what we have in this place. All these routers are in the same area. But the question should be, how do we know they're in the same area? We put them in the same area. By the time we start our configuration, you are going to see, we are going to tell this area, you are in area, this interface, you are in area 0. This interface, you are in area 0. This interface, you are in area 0. By the time we put all the interfaces on our router in area 0 by configuration, that means we are doing only one area. But what if I now have another router here now? Another router here, and decided to put this one area 1. I will tell this interface you belong to area 1. This other interface you belong to area 1. That becomes multi-area. So what will be the advantage of multi-area? We're going to see that. But for this class, we're going to only be doing only area 0. OSPF can be implemented in one of 2 ways as follows. Number 1, single area OSPF. That's what you saw here. All routers are in one area. What put all the routers in one area? The interfaces, we declare them to be in area 0. And the best practice is to use area 0. Why do you always have to use area 0? Area 0 is called the backbone area. Take note. You cannot have other areas without area 0. The journey must start from area 0, and that is the standard. The next one is multi-area OSPF. Like what I did right now, I added area 1. It has become multi-area. OSPF is implemented using multiple areas. In hierarchical fashion, all area must connect to the backbone area. Take note of this. This is key. All areas must connect to the backbone. What does that mean? This my area 1 has a direct connection with area 0. Can I have another set of routers here and call this one area 2? If we take a look at it here, this area 2 does not have direct connection to area 0. This is not going to work. I must find a way to come and put area 2 somewhere here, because it has a direct connection to the router that has one leg in area 0. That is what they mean when they say all areas must connect to backbone area. You don't know, you are not doing multiple area. I just need to point that to you. So just take note of that. Routers connecting the areas are referred to as area borders router. So if I have another router here, and I've decided to put this place in area 1, this my router becomes a border router. It's like a custom officer. If I have another router here, and I decided to put this one in area 2, this router here that connects area 0 to area 2, it becomes ABR. area border router. But the focus in this class is a single OSPF, single area OSPF version 2. We're going to talk about it, discuss all the theory, and then do our lab. Any question? Can I proceed? Okay, thank you. Thank you. Thank you, guys. Thank you. Okay. Thank you. So multi-area OSPF, I just gave you an example of multi-area. Look at another example here. They have these routers in area 0. This section, area 51. This other section, area 1. This is a good example of multi-area OSPF. So what is the advantage of multi-area OSPF? I won't be able to go in depth into this because it's beyond the scope of this class. Smaller routing tables. Tables are smaller because there are fewer routing tables entries. This is because network address can be summarized between areas. Route summarization is not enabled by default. These are CCNP stuff. But let me just give you this idea. All the routers in area 1, we only know about networks that are in area 1. All the routers in area 0, we only know about networks that are in area 0. All the routers in area 51, we only know about networks that are in area 51. That will give us smaller routing table because I don't have to know about all the networks. What if somebody now in area 1 needs to talk to somebody in area 51? They use default routes. That's beyond the scope of the class. So we are able to achieve smaller routing table. The next one is reduce link state update overhead. Now, link state advertisement, I'm going to show you from the video. You will see each of these OSPF routers, we keep on sending link state advertisement at the initial stage when we set it up. But when you have the concept of area, link state advertisement from area 1 does not enter area 2. It's not like broadcast, please, when we talk about segmentation. But this is a segmentation in a way at layer 3. And this is always used for big networks, big organizations that have like 500 routers, 10,000 routers, 20,000 routers. So they will now segment different routers into different areas so that they can reduce the size of the routing table. Then they reduce the link state overhead. That is the consumption of the bandwidth. And another benefit of multi-area is to reduce the frequency of SPF calculation. Because if there is a change in area 1, a network went down, all the routers will process that information. If you have 10,000 routers, they all need to process it. But if there is a problem in area 1, one network went down, or network is just added, it's only the router in area 1 that will process it. Area 0 don't care about that problem. And the same thing applies to area 51. They don't care about that problem. So it's a way to maintain stability when you have a very big network. That is where they use multi-area OSPF. Small networks, you don't need that. So when you talk about OSPF version 3, what comes to your mind? This one we've been talking about now is version 2. I've just summarized that for you. I say anytime you hear OSPF version 2, that means we are going to implement that with IP version 4. Then once we talk about OSPF version 3, we are going to have to implement with its IP version 6. Version 3 works with IPv6. Version 2 works with IP version 4. So let's go to the video that I promised to show you guys. So we'll now break down these packets down one after the other. Sorry, I need to stop the sharing. I forgot to log into the platform before now. That is on the academy. But I will do that quickly and show you guys. So let me share and then play the video. Nah, this is not the one I want. First one. Just a minute, guys. Okay. See you here. So are we ready? I want to play the video, so listen actively and check out all these packets.
Hello everyone, let's jump into OSPF packets, and we get to talk about these link state packets that have a couple cool functions. To start off, we've got the type 1 packet, and this is known as the hello. The hello is used to establish and maintain adjacencies with other OSPF routers. Your OSPF router is going to say hello to another router on a link. This is used to discover those neighbors and build those adjacencies, which are being used with keep alives to keep track of the neighboring router. The next one is the type 2, and the type 2 is the DBD. That's the database description packet. This contains an abbreviated list of the sending router's link state database. It is used by the receiving router to check its link state database against the sender. These link state databases must be identical between both routers within the same OSPF area. Our type 3 packet is the link state request, known as an LSR. And this is used to request more information from another router about an entry in the database description message. The type 4 is the link state update. This is what we send as a response to the LSR. Someone sends you a link state request, you respond back with a link state update. You're announcing either new information or you're sending what was requested from the LSR that you received. Now, a link state update can contain several different types of link state advertisements, known as LSAs. Type 5 is going to be the link state acknowledgement. The LSAC is actually able to acknowledge every other OSPF packet type except for a hello. You don't ACK a hello. And also we don't ACK an ACK. Those would be a forever acknowledgement going back and forth. So link state acknowledgements are awesome for acknowledging other packet types that aren't hellos and aren't acknowledgements. So let me jump into the OSPF link state updates. And first we're talking about those type 2s again. That type 2 database description packet, that thing is an abbreviated list of the sending router's link state database. And this is important because then we have that request, which is going to come up from another router saying, I saw your database and there's a specific item I need to know more about. And then we come to this, the link state update. That update is going to be in response to that request, or it's going to be an OSPF created message regarding a new network or something that's changed that's going on. Now, that link state update, as we mentioned, can contain many different types of link state advertisements. There's actually 11 different types of OSPF version 2 link state advertisements known as LSAs. I have them here on the right side. Now, these LSAs are the different message types that you might have a router receiving, which is part of an LSU. Now, in CCNA here, we really focus on 1 through 5, but we could go from 6 through 11, which is more of the advanced areas. So let's jump into an OSPF hello packet, and here we have it broken off into two sections. We've got the OSPF packet headers section itself and the OSPF hello packet section. Now, just a key reminder here, the hello packet is used to discover our OSPF neighbors and to literally maintain neighbor adjacencies. We've got a keep alive coming into play with this idea of a hello packet. Also, these hello packets include parameters that must be agreed upon in order for two OSPF routers to actually become neighbors. And lastly, when these hello packets run back and forth between two OSPF routers, they're also used in the election of the DR, the designated router, and the BDR, the backup designated router. This is only on those multi-access networks using technology like Ethernet. Point-to-point does not use DRs and BDRs. So let's talk about some of these fields. Here inside of our OSPF packet header, we've got a couple different things that come into play, such as type. And the type at the top is going to inform our router if it's going to be a hello packet, a DVD, an LSR, an LSU, or even an LS acknowledgement. We've got the router ID field, and that is going to have a 32-bit value in dotted decimal notation. It'll uniquely identify the router that's created this hello message. We've got the area ID, which is about the OSPF area number from where the packet originated. We've got the network mask, which is that subnet mask associated with the sending interface for this packet. We've got the hello interval. That hello interval is going to literally specify the frequency in seconds at which the router sends hello packets. Now that default timer on multi-access is 10 seconds. We're going to have the router priority. This is used in that DR-BDR election that we mentioned. The default priority for all OSPF routers is 1. This can be manually changed though. This is values of 0 to 255. The higher, the better in becoming the designated router, which is the DR. We've got the dead interval, which comes back into play with timings, and this is the time in seconds that a router will wait to hear from a neighbor before it says, "You neighbor are dead and out of service." By default, the dead interval is 4 times the hello. If the hello is commonly 10 seconds, the dead is commonly 40. The designated router, that DR, this is the router ID, the label name of the DR. The BDR, this is the router ID, the label name of the BDR. And lastly, list of neighbors is just like it sounds. This identifies the router IDs of all adjacent OSPF routers.
Okay, so that is the end of the first video. So I'm going to just summarize those packets again. Let me go back. So here, there's one thing I didn't talk about. They call this one type 1. They call this one type 2. They call this one type 3. They call this one type 4. Call this one type 5. This is used to maintain adjacency, meaning you want to be sure that your neighbor is alive. You keep on sending message periodically. But if you don't hear from, that's what there's something called LO interval, meaning the period in which you're supposed to be sending the hello message. But what if you don't hear from your neighbor? There's an agreement. If I don't hear from you within a period of time, we're going to see the timer later, I will declare you dead. You're no longer my neighbor. We have another one called database description. Is to compare what you have in your database, because all of us are supposed to have the same information. We're supposed to synchronize. So I will send you what I have, you send what I have, I will compare yours with mine and then update. If for any reason I see that you have something I don't have, I send information to you using type 3, link state request. I saw something like this, I don't have it. Can I have it? You reply back with me, sending link state updates, telling me or giving me the information that I'm looking for. And don't forget, there are different kinds of information that you can give to me. That's what you saw. Link state update packet. Those ones are plenty again. 11 of them. So it depends on what I am looking for. And by the time I get that message from you, I reply back to you with link state acknowledgement packet. Thanks, I got the message. These are the ones you are going to be having between the OSPF routers every time. All of this is just to make sure that our routers database are up to date as far as OSPF is concerned. So you can go to the platform and watch the video again and again, or watch my recording for you to get more of that information. I don't know if that clear to you guys. Hello packet, database requisition packet, link state request packet, link state update packet, and then link state acknowledgement packet. These are the packets sent between the routers to exchange information. Thank you, Aniola. I didn't know you are in the house. Yeah, Ali, thanks. Ali, thanks. I saw the message you posted on the platform. You are doing a great job in this class. I will miss you when we are done with this program. So that's just one video. I'm going to also play another video later. So this is what I've just, this is just a summary. The LO packet, database, link state request, link state update, and link state advertisements. You need to be aware of that. So this is one of the things they explain. Under link state updates, it could be update about router link states advertisement. It could be update about the database. It could be update about the link. It could be any of the updates that you are requesting for. So when the person is sending this, you can send LSA type 1, meaning it's giving you update about router LSA. LSA type 2 is giving you update about database synchronization. LSA type 3 or type 4 is giving you update about. So when you come to this link state update, plenty of updates can be given. 11 of them can be given. So, and when you are requesting, you are going to request for one of these updates. So you need to be aware of that. The router is going to reply with any of those things. That is the summary. So we saw also the packet. If we grab our packets with Wiresharks, we're going to see exactly the OSPF packet header and the IP. This is the part that points to the OSPF. Of course, our IP will always be there. Our frame header will always be there. Refer back to OSI model. You are going to see all of this thing there. But there's something the guy mentioned in passing, and I know you won't understand. He mentioned DR and BDR. I'm going to come to that later. DR and BDR. What is a DR? What is a BDR? These are terminologies under OSPF you need to be aware of. So I will come to that later. So we can't just pass all of those stuffs here. So the next part is OSPF operation. This is one of the reasons why I said people don't like OSPF. Too many stories about OSPF. So when we say OSPF operation, what does that mean? Let's watch another video and come back here. So I need you guys to listen attentively, because when I come to the configuration on Wednesday, you're going to now see some of these things at work. So this video is going to talk about the 7 states of OSPF operation.
So we're here to discuss OSPF operational states, and the key focal point is on the progression that OSPF takes from beginning and activated on an interface to having multiple OSPF routers reaching convergence. And to complete this convergence, we have 7 states to go through. OSPF will transition from a down state to an init, from an init to a two-way, from two-way to xstart, from xstart to exchange, exchange to loading, and finally loading to full. We're going to walk through these states as we go through, so let's get started. When we first begin our discussion of OSPF and these operational states, we need to focus on OSPF activation. OSPF is going to be enabled on an interface. And when OSPF is enabled on an interface, your OSPF router must then determine if there's another OSPF neighbor on that same link. And to do it, we start in the down state. And then when we go to send a hello, we're going to start to initialize. And we say hello to a multicast target of 224.0.0.5. My router ID is 172.16.5.1. That's a 32-bit value from router R1. And it asks, is there anyone else on this link? Well, in order for us to stay in the initialize state or init, we need to get a response back. Because right now, we're going from OSPF has been activated, we're in a state of called down, to initialize by sending a hello. Now, when we get a hello back, we stay in the init state because we have seen someone else on this OSPF activated link. We've received a hello from R2. Also, R2 has added information into its message saying, I have a new neighbor. I have a neighbor known as R1. They have IP address 172.16.5.1, and they exist off of my interface gig01. When R2 sends its hello back, it's responding to us, and it's going to be sending it as a unicast targeting our router 1 IP address of 172.16.5.1. Now the neat thing is, since R1 has received a hello back from R2, and R1 sees itself in this neighbor list of R2, we're going to transition to the two-way state. R1 has received a hello from router 2, and in that hello it includes R2's neighbors, which also is R1. And since we see our own router ID in R2's neighbor list, we can transition to what's known as the two-way state. Now, with this two-way state, we want to talk here about an election that will occur, and this election is for a DR and BDR role-based routers. This election only occurs on multi-access networks such as using Ethernet. In this election, our routers will have a default priority of 1 on their links. And because the priorities are both defaulted at 1, it's a tie. So the tiebreaker goes to what's known as the highest router ID. In this case, R2 has 172.16.5.2 as its IP address, and that is its router ID it's taken. It has the higher router ID, so R2 will become the designated router. R1 has a lower router ID because it has a lower IP address. It is 5.1. That would be the backup designated router, known as the BDR. Our routers will then move onwards from the basics of that two-way state and the election, and they're going to go on to what's known as their synchronization process for their OSPF database. What we're focusing on here is synchronizing their link state databases, which is really their topology table. And to start this synchronization process, we use the XStart state. And the XStart state, this is the exchange start state. We have our routers choosing who's going to share their link state database first. Now, that link state database is known as the DBD packet, which is going to be a summarized form of their link state database. And in that exchange start state, the two routers pick out who goes first, and then the router that says, all right, I have the highest, so I will send my database description packet over to R1. Now, the cool thing is, it's a summary. It's a link state database, and the R1 router is going to acknowledge that it's received that summary. OSPF likes to be reliable. R1 then sends its own summary of its link state database, and R2 says, awesome, cool, I've got your summary as well, and responds with an acknowledgement. After we have viewed each other's summary, their database description packet, the routers will then respond back to each other with LSRs and LSUs. An LSR is a link state request. We can ask for more information on specific network entries that we've seen in those DBD packets that we didn't know anything about. The other router that receives your request will then respond accordingly with an LSU, which is a link state update, saying here's the info you needed. And again, OSPF likes to be reliable, so we have the acknowledgement coming into play. Now, the cool thing is, after all those LSRs and LSUs, you've reached full convergence. So let's take a step back. When we have this DR and BDR relationship coming into play in that two-way state, why is it there? Why is it important? Well, what we have are multi-access networks. And multi-access networks are commonly when we have Ethernet connectivity in between our routers. And in this case here, we have 4 routers with a switch interconnecting them. So what's the big deal? Well, this is going to create multiple adjacencies. What we have here is every router has an adjacency with every other router. What that really means is every router is making sure it has a full converged state between itself and the other 3 routers. This is insane as it gets into larger and larger topologies with more and more routers. Because with every extra adjacency, we now have excessive link state advertisements, which are messages in between our routers. Also, if there's any change in our network, we're going to have extensive flooding. So let me show you. So router R2 here has a change, and it sends out its link state advertisements notifying all of its other adjacent routers, which is all other 4 routers. Now, those routers do their job, and they also notify all of their adjacencies that they've made with other OSPF routers. Now check it out here. OSPF is doing its job. It's doing it correctly. But look at all the excessive LSAs where each router is notifying every other router. What if we could do it better? Well, we can. By having a DR and a BDR elected inside of a multi-access network, we can have our router 1, router 4, and router 5 literally have a full state only with the DR and BDR. And router 1, router 4, router 5 will only have a two-way state with each other. They won't concern themselves with having the exact same topology table as each other router. So let's see what happens. So R1 has a change. R1 only notifies the DR and the BDR, saying, I have full convergence with you, here's the change. From there, the DR accepts that change, and then it notifies all of its routers that it has a full state with, which is everybody. But routers 4 and 5, they don't notify each other because they only have a two-way state with each other and a full state with the DR and BDR.
Okay, so let's summarize this again. Ali is asking a question. Let me read this question. Where is all this data stored in the RAM or separate file is created. The data is stored in the RAM. Ali, are you following with me? The data is stored in the RAM. That is one of the disadvantages of OSPF. If you don't have a solid router, a robust router, you cannot run OSPF on your network. The router will freeze. That's a good question. So the moment, there's still something I need to clarify on the DHAR and BDHAR. I'm going to come to that. But let me just walk you guys through this operation, even though you have watched the video. So the moment you have two routers together like this, and they are connected, you want to run OSPF here, you want to run OSPF here, they are both at the down states because you have to activate this interface, put IP address, say no shutdown, and activate OSPF on the interface. The moment you activate interface, they move from down phase to init states. From init to two-way, from two-way to X state, from X state to exchange, from exchange to loading, from loading to full state. So what happens at the down state? No hello packet is received, the interface is down. Router can send hello. How? You can send hello, but you can't receive. When I say the interface is down, no OSPF, let me say, no OSPF is activated there. No OSPF is activated there. That shouldn't be from the other side. It should be from the other side. Router sends hello packet. When you send hello packet, OSPF is activated, but you cannot receive hello. Yes, until you transition to init. At init state, hello packets are received from the neighbor. They contain the router ID. What is a router ID? That's like the identity of the router. And how do they get this router ID? We're also going to come to that, maybe in the next class. And then they transition to two-way state. Two-way state, what happened in this state? In this state, communication between the two routers is bidirectional. Now, on a multi-access link, what is a multi-access link? Take note of that word there, that multi-access. Let me explain that one to you. Anytime you have a connection on an Ethernet port, let's say now, let me connect this interface to a switch. This is our G0/0, it's an Ethernet connection. Why did they call it multi-access? If we like now, you can connect another router to this switch, and it's part of the network here. You can connect another router. You can connect another router. That is, Ethernet connection is multiple connection. Ideally, at the initial stage of networking, when people are setting up wide area network, they do not use Ethernet port, they use serial ports. So if we are using serial port between these two routers, this is not multi-access, it is called point-to-point. Point-to-point, face me, I face you. It is only two people that can be connected together on that connection. But the moment technology now begin to advance, and then they can now use Ethernet ports to link two routers together, the Ethernet connection by default is multi-access. Serial connection by default is point-to-point. So it's all about the port now. So when the two routers are connected together, the router will not believe that they are just the only two on the link. It will be thinking others are still going to come and join them. That is why they need to carry out election on DR and BDR. Why do they need to carry out election? If they do not carry out election, you saw the link state advertisement. This router want to form neighbor with this. The same router want to form neighbor with this. The same router want to form neighbor with this. Everybody want to form neighbor with everybody. And that is going to create a chaos on the network. And so in order for us not to have that chaos, they decided to have a president and vice president. Everybody forms neighbor with the president. If the president goes down, everybody form neighbor with the vice president. So if I have information to tell everybody on the network, I just tell the president will tell everybody because the president is my neighbor. So on a multi-access link, which means Ethernet connection, and when I say Ethernet, not just E, it can be fast Ethernet, it can be gigabit Ethernet, they are all based on Ethernet technology. There is always election because they believe that there are others connected on that link. So they always select DHAR and then BDHAR. Who becomes the DHAR? Who becomes the BDR? I'm also going to come to that again later. So our router will transition from two-way to X start state. On a point-to-point link, the two routers decide which router will initiate the database packet description. We saw that in the video, and decides upon the initial database packet sequence number. Somebody must send first, and it depends on somebody and the person that has a higher router ID. When they have exchanged their database packets and they've synchronized, they move to exchange state rather. Okay, no, from there they move to exchange. What happens at the exchange? Router exchange BDP packet, that is database description. If additional router information is required, then they transition to loading. Otherwise, they move to full state. So once the router moves to full state, the network has converged. The two routers have formed neighbors. They have exchanged information. Everybody knows about all the networks all together. But at the loading stage, what does that mean? You still have some more information you are looking for. You send link state request, and then you get link state update to get another additional information. When you have gotten whatever you are looking for, then you transition to a full state. This is what goes on behind the scene before you see two routers form neighbor, and they begin to be able to change information between themselves. And they get these things done using our packets, hello packet, database packet, and all of these things to go through all this operation. So you can watch the video again from the Academy platform. Is that clear to you guys? That summary, is it clear? Can I proceed?
Yes, it's clear. You can proceed.
Okay, thank you. For you, right? Others need to also confirm that. Okay. Okay, establish neighbor adjacency. To determine if an OSPF neighbor is on the link, the router sends a hello packet, we talked about that contain its router ID out all OSPF enable interfaces. Take note of that. We've been saying again and again, OSPF will be enabled on the interfaces, and you will see it on Wednesday. The hello packet is sent to the results all OSPF router. So this is the address you send the message to, and it will reach all the OSPF router. Take note of something here. The OSPF router ID is used by the OSPF to uniquely identify each router in the OSPF area. What is this router ID? How does the OSPF router get its ID? We'll see that on Wednesday. We can discuss that now. I don't know if it's still in the PowerPoint, but we'll discuss that on Wednesday, or we'll demonstrate that on Wednesday. A router's ID is a 32-bit number formatted like an IPv4 address, and it is assigned to uniquely identify a router among OSPF peers. So every single OSPF routers will have their own router ID. It's like their own identity. And we can allow them to pick that ID, or we can decide the ID for them. When a neighboring OSPF router OSPF enable router receives a hello packet with a router ID that is not within its neighbor list, the receiving router attempts to establish an adjacency with the initiating router. So he gets information from you. He doesn't know about you. He makes sure that he can get in touch with you and get to know about you. So we've talked about this. Down to init state, init to two-way. Then if it's a multicast network, they elect the DR and BDR, and so on and so forth. So what happens if you are stuck in two ways? Who are the people that will be stuck in two ways? Let me show you this. If you have 4 routers now, this doesn't make sense. All of them are connected to the switch. What for? I don't know why. This is R1. This is R2. This is R3. This is R4. If this guy is a DR, you know what's going to happen? Everybody is going to form neighbor with DR. So what happens between, let's say, router 2 and router 3? They will get stuck at any stage, 2 ways. They are not going to go beyond 2 ways because they cannot complete all the other processes that we've discussed about. This is a multi-access network. There's a need for election, and whoever wins the election, everybody forms neighbor with that person. So if you go and say you should show IP OSPF neighbor on router 2, you are going to see the DR as the neighbor. You are not going to see this guy as the neighbor because they are going to get stuck in two-way. After the two-way state, router transition to database the synchronization state. This is a three-step process as follows. We decide the first router. We saw it in the video. The router with the highest router ID. Router ID again sends its database description first. Exchange DBD, that is database description. As many as needed to convey the database, the other router must acknowledge the database with a link state acknowledge packet. So what happened? Then the router sends an LSR, that is link state request. Each router compares the database description information with their local link state database. If the database has more current information, the router transition to loading state, and you've already seen what is in the loading state. You request for more information. After all the link state requests have been exchanged and satisfied, the routers are considered synchronized and in a full state. Updates, link state updates are sent. How? When there is a change, when a change is perceived, there is an update that will be sent. Updates are sent every 30 minutes. Meaning what? Even if I don't have any new thing to tell you, I'll still tell you what I told you before, just for you to be aware or for us to be on the same page. I've explained this. Why do you need a DR? Because we don't want to create multiple adjacency, too many friendship. And look at the formula here. Let's take this formula and put this into consideration. If we have 1, 2, 3, 4, 5 routers on the network, these are the number of adjacencies that will be created. So n is the number of routers. Then n minus 1, that is 5 minus 1. So that is going to give us 5 minus 1 multiplied by 2 divided by 5. That is going to give us what now? No, not 5. Not divided by 5. Multiplied by 5. Is that n into n minus 1? Sorry, divided by 2. Sorry, this is not correct. That is going to be 5 into 5 minus 1 divided by 2. This is going to give me 5 multiplied by 4, which is 20, divided by 2. That is going to give me 10. What does that mean? Altogether, we are going to have 10 adjacency. This router want to form neighbor with this, you form neighbor with this, form neighbor with this, form neighbor with this. This router form neighbor with this, form neighbor with this, form neighbor with this. This router form neighbor with this, form neighbor with this. It's going to be a mess. They will consume the bandwidth completely. And that happens on the multi-access network. And they are going to be flooding the link state advertisement everywhere. In order for us not to have this, they are going to carry out election, select the president. Everybody form neighbor with the president. That is only applicable on point to point. But let me tell you something. Even if I have this kind of connection on Ethernet, I can go into the interface and say, I know you are multi-access by default, but begin to see yourself as point to point. And with that configuration, there will be no election. And we're going to do that in the next class also. So one more thing I didn't mention, what about the people that did not win the election? They are called DR orders. So you have DR, you have BDR, and then the rest will be DR orders. People that did not win election, they are called DR orders, other routers on the network. The BDR is the backup in case the DR goes down. So we're also going to come to that. And that is the end of my long story. I am sure you guys will be like, this guy did not even do any configuration.